So this whole chapter has been about radical functions and rational functions. And we've looked at the rational functions, we graphed them, we simplified them, added, subtracted them, solved them. And we just, recently, just in the prior lesson, looked at some things about radicals and radical expressions. So now we're going to be looking at radical functions, and we're specifically going to target the graphs of radical functions and inequalities, and we're going to transform radical functions by changing parameters. So we're going to be looking at transformations of radical functions this time. So it's rather than rational functions, we're looking at radical functions. So recall that exponential and logarithmic functions are inverses. That was basically the premise of the entire last chapter. Well, quadratic and cubic functions, they have inverses as well. If we wanted to look at the inverse of the quadratic function, which, by the way, the basic quadratic function is x squared, we'd be looking at the inverse of that, which would be the square root of x. And the inverse of the cubic function is the cube root function. So we're going to take a look at what those graphs look like, and we're going to look at some transformations of those graphs. So in our little diagram here, we actually have these two pairs of inverse functions graphed on the same coordinate plane. In this first graphic here, we have the quadratic function. So we have the parabola, the blue graph, that one we're very familiar with, the parabola. And we have its inverse, which of course is the reflection over the line y equals x, as all inverses are. And this time, so we have the parabola that's just turned to the side instead. So we've talked about what it means for something to be a function. If we look at that inverse of the quadratic function, which is the square root function, it's not a function. And that's because it fails the vertical line test. See, if I were to take and drop a vertical line down anywhere along that graph, except for at the vertex, it's going to hit 2 points. And so it's not a function. And we said that we're going to study radical functions. So in order to study this, we actually were going to have to restrict the domain. So we're going to look at just the part where x is greater than 0. So if we look at values of x, because we're looking at the square root of x here, right? If we looked at values of x that are greater than 0, we would just be looking at positive square roots. So we'd be looking at the positive values and actually 0. So actually we really should restrict the domain to greater than or equal to 0. And so then we would be looking at just the positive square root of x. Now looking at the other diagram, you'll see the cubic function. So we have this, the blue graph, that's x cubed, just raising different real numbers to the third power. And then the inverse of it is the cube root. So we take the cube root of, a positive number, we'll get a positive number. If we take the cube root of 0, we'll get 0. And if we take the cube root of a negative number, we'll get a negative. See, that's the difference between that and the square root function. We can take square roots of positive values and get positives, negatives and get negatives, whereas with that's cube roots. But if we took square roots of negative numbers, that wouldn't be real values, real number values. So that's going to have some effect on the parameters, like the domain and range of these functions, which we'll look at a little more in depth. So in general, a radical function is a function whose rule is a radical expression. A square root function is a radical function involving a square root. A cube root function is a radical function involving a cube root, and so on. So if we were to restrict that domain for the square root function to just when x is greater than or equal to 0, we get a graph that looks like this. So if we took just the parent function, we looked at the square root of x, which is the parent, and we plotted this on our graph here. So I would take, say, the square root of 0, and I get 0. The square root of, maybe we'll go with 1, I get 1. The square root of 4, I get 2. So I'm just kind of plotting out some of these points. Square root of 9 is, oops, I went too high on that one. That's supposed to be 2. And the square root of 9 is 3. And so that square root function in its original position looks like that. But now we're going to do a transformation of it. So this, if you had to kind of guess what's happening here, we know that we're subtracting 3 from the x, and usually if we change the x in this way directly, then that's going to cause a horizontal slide. So this is actually going to slide 3 to the right, and if we were to slide this graph 3 units to the right, and we took all these points and moved 3 units to the right, this is what it would look like. This point that was at 0, 0 would go 3 units to the right, it'd end up right there. This point, 1, 2, 3 units would end up right there. And then this point right here, 1, 2, 3, and that's about all I can fit on there. And that's going to be the graph of that function. So that function right there is the square root of x minus 3. Now, if I want to talk about the domain and range of this function, I know that domain means the x values. So if I think about the x values that I can't put in there, if you look at this graph, I mean, you look left to right on this, and you know that basically what happens is this thing stops right here, and there's no values up to the left of that line. There's only values to the right. And so if we had to talk about the values that are not in the domain, they're going to be values that are below that. So it's almost like that's an asymptote there. So the domain has to be values, if you think about it, have to be values greater than or equal to 3, because if we put 3 in there, we'll be taking the square root of 0. But if we put anything smaller than that, like 2 or 1 or 0 or whatever, we're going to get a negative number. So that's our restriction on our domain. Now, if you look at your range here, your values, the y values, they never go below the x-axis. So there's kind of like a line here that they don't go under. And so my range values are always greater than or equal to 0. And so my domain, the restriction is they have to be values 3 or up. So x is greater than or equal to 3, and the y values are greater than or equal to 0. So you look left or right to find the domain, and up and down to find and clarify and lay out what your range is. All right, so let's go ahead and turn the page and take a look at some more. How about a cube root function? So let's take a look at just the basic cube root function, and we kind of saw what it's supposed to look like on the other side. Let's think about some numbers. If we're going to make a table to graph this, or if we want to put that cube root, we could also do that in our calculator and get numbers from the table. But think about some numbers that are pretty easy to cube root, so perfect cubes. So when I think about perfect cubes, I think of things like 0, 1, I think of 8 as the next one, and then 27. The cube root of 0 is 0, the cube root of 1 is 1, the cube root of 8 is 2, and so on. So those are kind of some numbers that I want to pick, but I know that I can take the cube root of negatives too, so maybe I'll start with negative 8. So if I think about taking the cube root of negative 8, I get negative 2. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of 1 is 1. The cube root of 8 is 2. So I picked some values that I think turned out nice, and I'm going to plot these out. So negative 8 won't fit on there, but I know if I kind of extended my graph out here a little bit, 5, 6, 7, 8, it might be like right there. So I could go negative 8 and negative 1. There's a point. Negative 1, or I'm sorry, negative 8, negative 2. Negative 1, negative 1 right there. 0, 0. 1, 1. There's another point. And then 8, if I went out again a couple tick marks out this way and went up to 2, it would be like right there. And that way I can get the shape of that graph. It looks like that. It's kind of like that. It looks like a really stretched out S. And that's what the characteristic cube root function looks like. Let's talk about the domain and the range. Now, when you think about the domain, we look left to right, and what we're thinking about is there any values of x that I can't take the cube root of. That's what we mean by we're talking about the domain for this function. And the fact is, no, you can take the cube root of anything, positives, negatives, and so on. Remember the odd roots, you can take the square root of positives and negatives and 0. So it would be all real numbers. We'd say all reals. You could use the all real symbol or write the phrase all real. Now, the range. Notice that there really is no restrictions. This graph, although it's kind of pretty close to the x-axis, it's going to continue over time to just rise higher and higher and go lower and lower on the left-hand side. So we're going to get positive numbers out, which output is our range, and we're going to get negative numbers out, we're going to get zeros out, and you can actually see that in our table here that you get negative numbers, you get positive numbers, you get 0, and so that range is going to be all real as well. And in fact, any cube root function no matter what things we do to it to transform it or whatever, your domain and range will always be all real numbers because it's defined for all values. Okay, where we get into some problems where we have some areas where things are not defined is when we're taking even roots. And we looked at that example in the prior example where we had a restriction on the domain and on the range. So, okay, let's take a look at the next example. So example B is another cube root function, and I can tell that by just looking at this part right here, because you can see that the root that we're going to be taking in this function is a third root or cube root. So 2 times the cube root of x minus 2, and we want to graph this. So if we want to, again, kind of create a little table just to plot out some of these points, I mean, we could put this in the graphing calculator. You could get your values from that, or you could kind of just think about some things that are really easy to take the cube root of, like we talked about in the prior question. So if we wanted to take a cube root of -8, well, that's a perfect cube. -1, 0, 1, 8. Those are all the ones that would be near the origin. And so if we could try to manipulate so that this piece right here under the radical was -8 or -1 or 0 or 1 or 8, then that would work out perfect. So I just started kind of thinking about values that would make -8 under the radical. And I know it's something minus 2. Well, if I had -6 minus 2 would be -8. So then if I plug that in, I'd be taking the cube root of -8, which is -2, and multiplying it by 2, which would make -4. But again, I mean, you could easily put that in your calculator and then take some nice integer values from the table. And so then the next value I saw in the calculator table was 1, and that's because 1 minus 2 would be -1, so I'd be taking the cube root of -1 and multiplying it by 2, that's -2. If I were to plug in the next one that looks nice on the table is when I plug in 2. 2 minus 2 is 0, cube root of 0 is 0, times 2 is 0. The next one I thought worked out nice was a 3, so I plugged in 3 minus 2 is 1, cube root of 1 is 1, times 2 is 2, and then finally I could think about putting in 10, because 10 minus 2 would be 8, cube root of 8 is 2, 2 times 2 is 4, but that's going to be difficult to fit this on our graph anyway. So now if I take these and plot these points over here, so if I plot -6, -4, so right here, and then 1, -2, so 1, -2, right here, 2, 0, right there, 3, 2, here, and if I know what that curve looks like, that cube root function, it's kind of like that sideways cubic function, or the sort of like the S, stretched out S, it's going to look something like this. Now again, when we talk about the domain, we think about what values can we put in for x, and really there's no restriction on that again, and we said the cube root functions, the domain will always be all real numbers. And that's because we can take cube roots of negatives, positives, 0, anything, decimals, integers, whatever. And so with the range, again, if you look at this graph and you look high to low here, there's like no breaks in the graph that would, interrupt the flow of the graph up and down. And so I can tell that, again, the range is all real numbers. So we've got all reals, all reals. Now, so for this next function, I'm going to take a look at what the parent function would be for this, because that's kind of where we're headed next in this lesson, is to be looking at, well, how can we look at these functions and be able to tell what kind of transformations occurred from the most basic root functions, the cube root, square root, and whatnot. And so I think back to that first example where I looked at the square root of x, and I thought of some nice points like 0. If I take the square root of 0, it's 0. Take the square root of 1, it's 1. Take the square root of 4, it's 2. And I plotted those points, and I'm showing that graph here. So if you think about what we know about transformations, by taking this function, square root of x, and adding 2, you might be able to tell that what's going to basically happen is all of these points are going to go up 2 from where they were to start. So that's one way to graph it, is to graph the parent function, and that's just apply the transformation. So in this case, I could just take each of my points and go up 2. So there would be the first point right there. And then I go up 2 from the next one, which was at 1, 1. So now it's at 1, 3. So there we go. And then the next one that was at 4, 2 is now going to be at 4, 4. So there that is that, and then I connect it, and that's what the graph of that function is going to look like. Now to talk about the domain and range, again, think about the domain, the values that we can't have for x. Well, what we're doing to x in the function is taking the square root of it. So we know we can't have negatives, and you can see clearly that this way, on the x-axis, there are no values on the graph. It's just like cuts right off at 0. And so that means that the x values have to be greater than or equal to 0. Now with the range, we're looking up and down, and notice that there's no values below that lowest point right there. That's on the y-axis. And that means that that point, whatever that point is, which that point is at 2 on the y-axis, that is as low as it will ever get. Because if we, we're just never going to get, the smallest square root we could take is the square root of 0, and then if we added 2 to it, that smallest value we'll ever get is 2. So that means in the range, the y values will have to be greater than or equal to 2. And so essentially what happened here in this graph is this was a vertical shift, or a vertical slide, up 2. Let's go ahead and turn the page. So as I mentioned in that last example, we're going to take a look at the general format for transformation of these radical functions. And so this right here, it would be sort of like that general format, or that standard form of a transformed radical function. So let's take a look at what each one of these things means to the graph. Well, the A out in front, remember that actually, the A out in front, which you want to be careful, does not actually represent the index, so just be careful about that. That A out in front is like a scalar, like a number being multiplied by the function, and so that will cause, as usual, a vertical stretch or compression, depending on whether the number is greater than 1, which would be the stretch, or between 0 and 1, and that's the compression. And then if there were a negative out in front, that would cause the reflection over the x-axis. So just as usual, that number out in front will affect the stretch and compression vertically, and also the position vertically in terms of whether it's reflected or not. So it could also be reflection across the x-axis. Next thing that kind of just jumps out at me is the plus k off the end. And remember, that's when we've looked at other transformations of functions, that adding or subtracting off the end of the function, that causes a vertical translation. So slide up or down. Going into where the x is, which is under the radical, and directly adding or subtracting from it, that's going to cause a horizontal translation. And remember, it's kind of the opposite of what we think. X kind of lies to us. If it's as an x plus some number, that really means it's actually moving to the left. And x minus something means it's moving to the right. And then as per usual, anything that you are multiplying the x directly by, which since we're under the radical, we're going right and focusing on x to multiply by, that's going to cause a horizontal stretch of compression. And so this b, with whatever your scale factor is for a horizontal stretch of compression, if you multiply x by the reciprocal of that, that's going to cause your horizontal stretch or compression. So all in all, it's very, very consistent with what we've seen for other types of functions. And now this particular one shows a square root function, but this could also be a cube root function, a fourth root function, or anything else. And so when you first of all, you got to look at whatever root you're taking, and then that way you'll know what the basic parent function is, whether it's that sideway s or it's just that one branch of the parabola turned to the side, and then transformations will occur from that parent function. So what I like to do with these is I start off with that parent function, and then I just apply the transformation, and that's definitely a viable way to do that. So if I look at example A, in example 2A, they're wanting me to graph the square root of x plus 5. So that's similar to the one I just did on the prior page, and its parent function is this. It's the square root of x. So what I might do is I might start off by graphing that, and I graph that by the points where I'm just taking the square roots of whatever my input or my x value is. So if I substituted in negative numbers, I couldn't take the square root, so I'm not going to start with any negative numbers, and that tells me that the domain doesn't contain negatives. And so if I put in 0, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of next one that would be easy to put in is 9, and that's 3, and so I could graph that parent function right here. So that's that square root of x, and then the plus 5 off the n is going to cause a vertical slide up 5. So to graph my new function, I'm just going to count up 5 and plot a new point. So up 5 from 0 is at 5. Up 5 from 1 is at 6. Up 5 from 2 is at 7. And up 5 from 3, excuse me, is at 8. So then I just draw the curve, and that's my new function. That's the square root of x plus 5, or what we called g of x. Now if I use that same strategy with example B, again I want to start off with whatever the parent function is. So this is the parent function, so you want to write that down, and that just means this is going to be some sort of transformation of the square root of x. And so I always put that on my graph first, so I'm going to plot those same points out for the square root of x. So that means 0, 0, 1, 1, 4, 2, 9, 3, and get my parent graph on there. So this is my square root of x. And then I'm going to take a look at what they did. Well, they multiplied by a half out in front. So we know that if you multiply the function by some scalar value, then that means that's going to be a vertical stretch or compression. In this case, this one is a vertical compression, and that's because the number is between 0 and 1. So it's going to compress it down back towards the x-axis. And so if we wanted to use the same strategy of just applying the transformation to the parent function, what that really means is every one of these points is only going to be half the distance that it was before away from the x-axis. So like for instance, the point that's at 0 is still at 0 because you can't get any closer than 0. But the point that's at 1 would be right here at a half. The point that's at 2 would only be at 1. The point that's at 3 would be at 1.5. And so these points right here that I'm plotting on the graph now, if I connect them, that's what the graph will look like. And you have to kind of be careful that you get it so it doesn't look like a line, but that is definitely a curve, and that's 1/2 times the square root of x. So you can just see how it was compressed down back towards the x-axis. So now let's see if we can take a look at some more complicated transformations in terms of their functions, and see if we can describe what's going on in terms of how it's changing from the parent function. So I know that this thing is the square root of x, so I know that that's a transformation of the square root of x, and I'm going to tell what each thing does. So first of all, I have a negative out in front. So that negative out in front, remember, is a reflection over the x-axis. It's going to change its position vertically. It's going to flip it from being above the x-axis to being below. And then the 3 part, that part right there, that's a vertical stretch because that's being multiplied by a number greater than 1. So it's a vertical stretch of 3, factor 3. And then finally, this part right here, the -1. Now notice the -1 is not under the radical. So that means it's a slide down 1. It's a vertical slide if it's not under the radical with it, if it's off the end. So it's a slide down 1. So I want you to go ahead and pause the video, and we're going to make example B a you-try question. So see if you can look at the graph of square root of x and see how it's transformed in this new function g of x. So please pause the video now. So that one was a reflection over the x-axis in a slide 4 units right. Now this was a slide horizontally because the subtraction or addition actually occurred underneath the radical with the x. So when you go in and change x directly, and you can kind of even think about this as actually having parentheses around that, what's under the radical. And then you can clearly see that it is grouped together with the x under the radical. All right, let's go ahead and turn the page. So we've reached our last learning goal, and our last learning goal is to write transformed square root functions. So we could do this with cubic functions, or cube root, functions, or fourth root functions as well. But we're just to, since they all sort of work the same, we're just going to stick to the square root functions. And so we're going to assume that in every case, the parent function is the square root of x, and we're going to apply transformations from that base position. So it's an example A. It says use the description to write the square root function g, and then it says the parent function f of x is equal to x square root of x, and it's reflected across the y-axis. Okay, so this time it's reflected across the y-axis, which would be a horizontal reflection, and vertically stretched by a factor of 7, and then translated left 5 units. So let's see if we can kind of put this all into a function. So let's take a look at the first thing is it says the reflection over the y-axis. And usually it's a good idea if we do that at the end. And we talked about that in a prior lesson where sometimes those horizontal reflections and compressions and stretches, we usually want to kind of save those to the end. So let's go ahead and first look at the stretch vertically by a factor of 7. So we know that vertical stretches will occur out in front. So if we put that out in front, and then we have our square root. So we know this is going to be a parent function of the square root of x. So then we translate, if we want to do the part where they translate 5 left, I know that x lies to me, so I'm thinking x plus 5 because I've got to go to the left. And so normally I would think x minus 5, but that means it's got to be x plus 5. And then finally the reflection over the y-axis. So that means I have to go in and where the x is, take the opposite of that. So that means I'm going to have to take and put a negative right in front of this part that's underneath the radical, in other words, the radicand. So I'm taking the opposite of this whole thing. Now, so, say I want to check to see if this is correct or not. So I'm kind of worried that, especially when there's horizontal things like the reflections in the slides. And so I went ahead and put this in my calculator, and this is a picture of what the graph looked like. And so you can see that this is the graph, and the original is over here. This is the parent function. I put that on there also. And you can clearly see each of the things that was supposed to happen happening. You see the reflection over it went over that y-axis, so it's now instead of in the first quadrant, it's in the second quadrant. You see it's definitely been stretched vertically. It's much higher up away from the x-axis. And so the plus 5, that did what we wanted it to do, which is moved it 5 to the left. So it reflected it and moved it 5 to the left, and there's my final function then. And the graph verifies my answer. Let's go ahead and try another one. So this one says, use the description to write the square root function g. The parent function is the square root of x. It is reflected across the x-axis. So we've got these things going on x-axis, compressed vertically by a factor of 1/5, and translated down 5. Now this is my favorite kind of transformation. Everything is a vertical transformation, and those are always very straightforward. So to reflect over the x-axis, okay, I'm going to put a negative right out in front. We know if we put a negative out in front, that's going to reflect it over the x-axis. Compressed vertically by a factor of 1/5. So vertically, if I want to compress it by a fifth, means it's going to basically push it back towards the x-axis. And so I put the 1/5 out in front. I've got my base function, which is the square root of x. And then since I'm going down 5, I have to subtract 5 off the end. So that's what I think my function is. And again, it's a good idea to graph these things and verify by looking at what actually occurs when you apply these things to it. See if it did what it was supposed to do. So I graphed it, I took a picture of what it looks like, and here it is. So here you can see that the original parent function is right here, and it's been reflected across the x-axis as we needed it to do. It's been compressed, and you can actually see, if you look at the new graph down here, it looks much flatter, and that's because it had been compressed. And then it was slid down 5. So you can see that starting point of that graph is moved down 5, and so it all kind of goes along with what the description of the transformation involved. And let's try one more together, and we'll have one for a you try. So this time it says, use the description to write the square root function g. The parent function is the square root of x again. It is compressed horizontally by a factor of 1/5 and reflected over the x-axis. Well, the reflection over the x-axis, that's easy to apply. So we just take and put a negative out in front. That's going to reflect it over the x-axis, because x-axis reflection is a vertical reflection. But then the horizontal compression. So remember, with the horizontal compression, we have to multiply x by the reciprocal of the scale factor. Well, x is under the radical. So if I go under here with the x under the radical and I multiply by the reciprocal of that scale factor, well, the reciprocal is 5. So I'm going to multiply x by 5, and that should give me the correct transformation. So again, I took a picture of it, graphed it. I encourage you to do the same. And this is what it looked like. So you can see the parent function there. You can see the new function. And, you know, sometimes when you do a horizontal, so you see the reflection, but sometimes when you do horizontal compression, if you think about pressing it towards the y-axis, you're kind of compressing it in, it actually makes it sometimes look like a vertical stretch. Because, you know, basically like by pushing the higher points in closer, it actually just makes it look like it's stretched vertically. So that actually jives with what we wanted it to do. So that the graph again verifies what our function turned out to be. So what I'd like to have you do is pause the video now, and I want you to give this a try, and maybe give a check on your graphing calculator and tune back in to see the final answer. So please pause the video now. All right, so checking this one was a little bit tricky. Hopefully you got the function square root of x plus 6 under the radical and then plus 9 off the n. So the plus 6 moves 6 left, and the plus 9 off the n moves 9 up. And so if you look at the parent function here, and you can just barely see the transform function up here, but you can see it definitely moved it left and up so far that if you have a standard window, you're not going to see the whole thing. You'd actually have to expand out your y-axis to be able to see any more of it. But those are pretty good clues that we've got the right function. So that actually does it for today's lesson. So I'll see you in class.